Now let's look at some AP style continuity questions. We want to find the value of k so that f of x is continuous everywhere. So f of x is this piecewise function, which we know we can run into some continuity issues with piecewise functions. So this one is the horizontal line 2 for x values less than or equal to 0. So this piece of the piecewise function 2, well, 2 is a linear function. It's continuous everywhere on its domain. So this left side of the function for x values less than or equal to 0 is going to be continuous. And the second piece of the function, x squared plus k, for x is greater than 0, we know that a quadratic is going to be continuous everywhere on its domain for x values greater than 0. That's this portion of the domain that applies to x squared plus k. So the real issue here is that the problem would occur at the x value 0. So we want to make sure and clear up that issue and find the right value of k so that there is no jump or hole in the graph at the x value 0, because 2 is always going to be continuous. A quadratic is always going to be continuous. And so we just want to make sure that we fix the problem or potential problem with the x value 0 in the transition between the two pieces of the piecewise function. So let's go ahead and analyze this problem graphically first. So 2 is a really nice, easy function to draw, just a horizontal line at 2 for x values less than or equal to 0. So 0 on the x-axis, less than or equal to, meaning that I need a filled-in circle at that location. So here is my first piece of the piecewise function. So now the second piece of the piecewise function, any parabola is going to be continuous, again, on its domain. So we want to make sure and choose the correct y-intercept. So this type of quadratic, x squared plus k, is in the form for when we decide this value of k, it's actually going to be just its y-intercept. So we want to choose the right y-intercept so that it perfectly coincides with where we left off on the horizontal line 2. So this one, hopefully you see as a pretty easy problem. I'm going to need my y-intercept, my k value, to be positive 2 because I want to pick up where I left off. So I want my piece of the parabola to pick up at 2 at again that potential problem value 0, where I switch between the two pieces of my piecewise function. So this left side, y equals 2, was already a continuous function for x values less than or equal to 0, and x squared now plus 2 is going to be the only function that would satisfy the transition so that the remainder of my function is continuous, so I'm continuous from negative infinity to infinity everywhere. So the k value is positive 2. So that's sort of taking a look at it from a graphical perspective, really just sort of filling in the hole or the potential hole. So this portion of the graph is y equals x squared plus 2. So a quadratic shifted up 2 units so that I can make sure and pick up where I left off from the horizontal line. But now let's go ahead and analyze this from a calculus perspective. So in order for a function to be continuous, we need to make sure that the limit from the left equals the limit from the right, again, at this point 0, where I'm going to have that potential problem. So I'm going to need the limit from the left side of 0. Well, if I'm looking at the left side of 0, then I'm going to have to consider the piece 2 of the piecewise function. And I need that, so I'm forcing that to equal the limit as x approaches 0 from the right, which means that I'm looking at the function x squared plus k. So I'm going to need these two pieces to be equal, and then more than that, I'm going to need the limit from the left to equal the limit from the right to equal the function value at 0. I need all of this to happen in order to have continuity at 0, which again is the only real potential problem location. So now I need to solve each of these limits. So this first one, if I have the limit of a constant, that's just a constant. That's just 2. And now here, I can really solve this using limit laws. So I will actually break this down. The limit as x approaches 0 from the right of x squared plus 0 from the right of k. And this, I can use the power power limit law, so this is really just the limit as x approaches 0 of x all squared. And this is, of course, just 0. And this is a constant, just like 2 was, so this limit here is k. So here's what I have. I have 2 equals 0 plus k. And again, all of this needed to equal f of 0. So we can actually find f of 0. 0 is included in the first portion of the piecewise function, so it is exactly 2. F of 0 is 2. So 0 plus k, well, that's just k. So what we have sort of on both ends here is that k has to equal 2. So in order for this to work out, my k value had to be 2, which again I was able to find graphically because these were two really nice functions to deal with. So it's really important to understand this in both ways, to understand what's happening graphically, that we're sort of going to fill the hole or make sure that there's no jump in the graph at this particular x value, and it was up to us to find the right k value that would work. So graphically this was pretty straightforward, and then this portion here is the calculus portion that you have to understand about it, that the limit from the left of 0 equals the limit from the right of 0. So far that could mean a hole in the graph at 0, but then setting both of those equal to f of 0 means that we fix that hole. So that would force the function to be continuous everywhere, because constants are continuous everywhere on their domain, and then parabolas are continuous everywhere on their domain, and we fix the problem or potential problem with 0. Alright, so now another piecewise function, same set of instructions. Find the missing value of k that makes this piecewise function continuous. So this one's just slightly harder than the last one. I have a linear function for the first piece of the piecewise function. I have x minus k for x values less than or equal to 1. So I'm going to need to find that k. Or really, I'm going to need to find the y-intercept, because this line is in slope-intercept form. And the second piece of the piecewise function is known entirely. I have x squared plus 2 for x values greater than 1. So we're going to look at this graphically first. And we're going to start by graphing the piece that we do know, x squared plus 2 for x values greater than 1. So x squared plus 2, that we just actually looked at that function. That's a parabola that opens upward with a y-intercept of 2. So I'm actually not going to be defined over here on the y-axis, because my graph is only defined for x values greater than 1. So if I plug 1 into this bottom piece of the function, 1 squared is 1 plus 2 is 3. So I'm going to go ahead and start my piece of the piecewise function at 0, 3, but I need to start with an open circle or a hole, because this is only for x greater than 1. And so it's going to look like this top part of a parabola here. So it would normally go through 0, 2 here, but I can't be defined for any values less than 1. So I'm just going to pick up right here with an open circle and continue. So this is x squared plus 2. So now my job is to find this k value, find the y-intercept, so that x minus k, this line with slope 1, fills this hole here. So remember that, again, this line has slope 1, and I want to make sure and fill this circle. So I'm just going to go ahead and start at this open circle with a filled-in point. And I need to be defined over here to the left of 1. So a slope of 1, well, it means up 1 to the right 1, but since I want to be defined to the left, I'm going to instead go down 1, and I'm going to go left 1. So here's a second point, and then down 1, left 1, down 1, left 1. So I'm going to go ahead and connect my dots with the line that I need. So this red graph here is going to be the line that makes this particular piecewise function continuous everywhere. So now it's a matter of figuring out, well, what do I need to substitute in for k, given that I just found my y-intercept is positive 2. So let's think about this. The equation of this line is y equals x plus 2. So again, it has slope positive 1, it has a y-intercept positive 2. But my piecewise function was of the form x minus k. So my value of k, I need it to be positive 2 in this position of a y-intercept. If there's already a negative right here, this value of k is going to have to be negative 2. so that what would end up happening is the minus and the negative will cancel and become positive. So my value of k here is going to have to be -2. So that one's just a little bit trickier than the last one because we might have thought, oh, well, the y-intercept is 2, so I'm just going to fill in 2. But this was in the form x minus k, so k actually needed to be -2 on this example. So that was, again, looking at it from a graphical perspective. But now let's take a look at it from the calculus perspective. We're going to need the limit from the left side of 1 to equal the limit from the right side of 1 to equal the function value at 1. So 1 this time instead of 0 because that's the potential place where I had either a jump or a hole in the graph. So we needed to make sure and fill that hole at the x value 1. So the limit as x approaches 1 from the left, the function there is x minus k. That has to equal the limit as x approaches 1 from the right of the second piece, x squared plus 2, and that's going to have to equal f of 1. So this, forcing this to be true, forces continuity at the value 1, which is the only place there could be a problem because the top function is linear, which is continuous everywhere. The bottom function is quadratic, which is continuous everywhere on their respective domains. So now we just solve each of these limits. We can do that using our limit laws. So the limit as x approaches 1 from the left of x minus the limit as x approaches 1 from the left of k. And then on the right side here, I have the limit as x approaches 1 from the right of x squared, or really, this whole quantity squared, plus the limit as x approaches 1 from the right of 2, and that's going to have to equal f of 1. So I will actually go ahead and write f of 1 here. By substituting 1 into this top function, 1 goes into the x value. So f of 1 here would be 1 minus k. So remember, I'm taking 1, that x value, and plugging it into the top function because 1 is with the top part of the domain, and I don't know the value of k yet. So now, on the left side, the limit as x approaches 1 from the left of just x, well, that's just 1, minus the limit of a constant, k is just some constant value is k, equals, now the limit as x approaches 1 from the right of x is 1, and that quantity is squared, plus the limit as x approaches 1 from the right of 2. 2 is a constant, so just 2. So k was just a constant, that's why we had k. 2 is just a constant, that's why we had 2. But when there's the x value, then it's whatever number we're approaching, so that's why those were 1s. And again, that has to equal 1 minus k. So now what I have is that 1 minus k has to equal, well, 1 squared, that's 1, plus 2 is 3. So this has to equal 1 minus k. So notice we have the same situation. So I'm just going to solve one portion of it. So I'm just going to solve for k using this left equation, because this is like two separate equations. It says 1 minus k equals 3, and then 3 equals 1 minus k. But I'm just going to solve this left equation because they're the same thing. So here I would subtract the 1 to the other side. So negative k equals 2, right, if I subtract 1 from 3. And then divide both sides by a negative, I get k equals -2, which is what we found when we analyzed the graph of each piece of the piecewise function. That's how we were able to find that y-intercept, but then we needed to do that additional piece and consider how we were going to make it work for what we were given. So this is an AP type of question. They love to ask the questions, find the value of k. Sometimes it will be the case where the graph is an option, but I cannot stress enough that you really do need to understand the formal calculus application. Of course, this is a calculus class. Of applying continuity at a point and understanding why, in this example, 1 is the x value that we needed to analyze. The limit from the left equals limit from the right equals f of 1, and the other example it was 0 because those were the potential places where we were going to have some type of problem.